Here for the session is Goksu Toga, who is at NC State. He's a postdoc at NC State University and has been working towards measuring OTOCs on Aquila.
All right, yeah, thanks for the introduction. So today I'm going to talk about information propagation in Rydberg arrays via fully analog OTOC measurements. So the initial pitch for this project was to investigate exotic information propagation and scrambling in neutral atoms using a model motivated from holography. So this is the model we had. It is called hyperbolic Ising model. So it's basically a mixed field Ising model with site-dependent couplings that's obtained from embedding this model into a ADS2 background, which is negatively curved. And these couplings follow a functional form of a cosine hyperbolic. And then we show that by using tensor network and some gate-based for conducting simulations. In the presence of this negative curvature, this model actually becomes a fast scrambler, meaning that the linear light cone that you would normally expect from a Lieb-Robinson bond becomes actually logarithmic. So you can use this model to study fast scrambling behavior with minimal simulation cost. So the idea was that we do this model on Rydberg arrays because you can easily map the mixed Ising model into a Rydberg Hamiltonian. But the initial step in doing this is actually develop a method to measure scrambling in Rydberg arrays. And so our first goal in this talk is going to be to actually measure something like this and extract the functional form of the light cone. So I've been calling scrambling, but what is scrambling? So there's many different complicated definitions of scrambling, but the way I like to think about it is the loss of information as the system evolves through time. A nice way of visualizing this is that you can imagine your initial system by just cracking a couple eggs in a bowl. Everything is nicely identifiable, and then you give this to your favorite quantum chef or your quantum system, which literally scrambles it around. In the end, you have a homogeneous mixture where all the information about your initial system is lost and irrecoverable. And the way different quantum systems achieve the scrambling distinguishes between different kinds of scrambling behaviors. At the top of the hierarchy, there are models called fast scramblers, which achieve the scrambling in the fastest way known and that is possible in nature. And these are models like black holes, SYK model, matrix model, our hyperbolic Ising model. Then you can use these models either in cryptography or studying quantum gravity or simulating black holes on quantum computers if you're ambitious. So how can you measure scrambling? So the go-to observables for measuring scrambling and information propagation are these observables called out-of-time order correlators. And as is evident from its name, the difference between this and a regular correlator is that these are ordered in an out-of-time fashion, where in a regular correlator, you would have the time-dependent terms in the beginning and the time-independent ones later. And here, the time-independent ones are interlaid within time-dependent operators. And the connection between OTOC and information propagation actually becomes more apparent if you go back to its parent definition, which is the squared commutator. If you look at this closely, you can see that the value of the squared commutator actually depends on the number of degrees of freedom this doubly acts on. At time equals 0, doubly acts only on one state and commutes with V that's located far away from it. So this gives you the double commutator as 0. But as your system evolves under time, double becomes more non-local, starts to commute with V. So this increase results in an increase in C. So by measuring either this double commutator or the OTOC, you can measure of this double operator or your information that you encoded the double propagates in your system. So, but you can say mixed field Ising model is much more easily simulatable in any other kind of quantum computing platform. You can do this with superconducting qubits, trapped ions, etc. Why do this on Rydberg arrays? So there are a couple of reasons for that. The first one is Rydberg Hamiltonian is a very rich phase diagram. And the effects of these different phases in information propagation and scrambling have not been explored completely. The second part is that unexpected phenomena have a tendency to come up in Rydberg experiments, like quantum scars, where they first found experimentally and then became a field of its own now. And then recently, this year, a group showed that if you look into the two-point correlation functions, you actually see some sublinear dynamics in the time evolution of these guys, where you would expect to see some linear light cone and then they attribute it to the atomic motion. So independent of our motivations for holography, developing concrete tools of measuring OTOCs on Rydberg arrays could lead to some interesting new phenomena that we didn't expect to see before. So there are many different ways of actually measuring these OTOCs on quantum hardware. Mainly, they've been developed in gate-based quantum computing. And the most straightforward way to do this is actually implementing the full operator. And if you work at Google, they have unlimited resources. That's the most straightforward way to do and gives great results. But if you worry about resources and you kind of have to cut down the number of shots and time you spend on it, there are various tricks of introducing ancillary qubits or performing different complicated interferometric approaches to actually measure these OTOCs. The method I like most and I have used in my work is to use randomized measurements to extract the information from OTOCs by doing some randomized averages over these two operators. So let's look into how this protocol works. It's been developed by Vermeersch and Peter Zoller's group back in Europe. And the basic idea is that you replace the trace over the infinite temperature density matrix by an ensemble average over CUE unitary. So what you do is, using that ensemble average, you break down the OTOC into two parts. Now you have just like a single time-evolved operator, and another one where the V operator is the time-dependent operator is sandwiched between two V's. And then you do a bunch of random samples over the CUE group, and then you calculate the correlations between these two measurements. And if you do this correctly, the decay of those correlations give you a measure of OTOC. And these randomized unitaries can either be applied globally, which is harder to do, or locally. But if, in the case of doing these locally, then you need to do another averaging process to go back to the original definition of the OTOC. So let's see how this works in action. So we implemented the local procedure on IBM Sherbrooke a couple of years ago. And we did perform the two parts of the measurement. Each of the red dots you see here is one single random sample. And what you expect to see here that when you start your experiment at time equals 0, these things needs to be highly correlated. So if you calculate the ensemble average, it's going to give you 1. As time evolves, these correlations are going to decay, which is going to result in a decay of OTOC. So if you actually go ahead and calculate those averages, you can see that this captures the dynamics of OTOC pretty well. So here, this black dots are the simulation, and red one is the error mitigated Sherbrooke results. And you can see that it agrees with the simulation very well up to 8 Trotter steps. This was done using 7 spins at the critical point of the hyperbolic Ising loop. So, but this is a talk about analog quantum computers. So let's go back to analog quantum computers. So if you consider NMR experiments in analog quantum computing, OTOCs have been done in NMR experiments for quite a long time and actually have been first developed in NMR experiments as a way of doing log-Schmidt echo sequence. And in this, specifically in the PXP limit of the Rydberg Hamiltonian, you can do some clever tricks and invert the sign of the Hamiltonian by just using a single pulse. But in general, the hard thing about implementing these OTOCs in analog quantum computer is that sign reversal operation that you need to do. So our idea was that what if we combine the existing randomized OTOC procedure with the idea that came from the same group that replaces these random global unitaries by randomized quenches. So they show that by doing randomized quenches, you can actually calculate Renyi entropies. And so, and they actually talk about in their papers that this is possible to do in the case of OTOCs too, but they never actually went ahead and did that. So our idea was to do that and measure OTOCs on Rydberg arrays. So the protocols look something like this. It's almost the same as the gate-based version, but now we're replacing this global unitaries by some randomized quenches and the gate-based time evolution by just some analog time evolution under the model Hamiltonian. And we do the same thing and look at the correlations between these two things. So if you do this in your experiment and look into the waveforms, this is what it looks like. So you start with doing your random quenches, which are these trapezoids. And then you implement your large detuning. You time evolve as long as you want, and then you measure in the end. I guess the disadvantage of this protocol is the high number of control parameters that you need to fine tune to extract something reliable. The first thing you need to decide is how long do you want to spend quenching your system. you have finite coherence time, so you want to optimize this so that you quench the system enough that you mimic that random evolution, but also you have enough time left to see the information propagation. So by trial and error, we figured out that 1 microsecond is enough to see these kind of things. So we usually cut our quenching time in 1 microsecond. Then you need to decide how many of these pulses you can fit during the 1 microsecond. And then experimental capabilities come in. We found that if you make these pulses more square-like, they behave better, but there's experimental capabilities. So the fastest ramp up and ramped up can do is actually 0.05 microseconds. So that's what we did. And then you need to choose the mean and the width of the Gaussian distribution you sample these quenches from. Then you have the pulse of the magnitude of the pulse V, which is not that important as long as it's something strong enough that disturbs your system and you have your usual Hamiltonian control parameters. But ideally, if you figure out the right combination of this works in any limit of the Rydberg Hamiltonian. So let's see if it actually does what we expected to do. So we did some simulations for that and performed the same analysis we did by using random quenches. So each one of these green dots is now a randomized sample. So at time equals 0, it does what we expected to do. The ensemble average is 1. And then as time evolves, these decay. So we're on the good track and right track to use these things to measure OTOCs on analog hardware. So before we go on and waste all our shots on some hopeless case, let's see what's the complete cost of this procedure is going to be. So the total shot cost for this, for producing one light cone picture, is 2 times the number of samples times the number of shots times time steps. So by some trial and error, we figured out that if we use a time step of 0.3 microseconds, 100 unitary samples and 100 shots with parallelization of 4, you can extract these light cones dependably that you can fit a line through them, which amounts to around 200,000 shots. And given that our allocation line is around 300, this comes up to perfectly if you account for the submission test that Amazon charges you to. So let's remember what we were doing. We have the Rydberg Hamiltonian. We set the distance to 9.5 micrometers so that we're close to the Ising limit and the nearest neighbor interactions are negligible. And then we just choose some delta and omega, which are like 1.5 and 2.5 megahertz. And now we kind of change our heat map plots that they're more in line with the experiment now. So we have the atoms on the y-axis and time on the x-axis. And then we kick this top spin with the large detuning pulse and see how it evolves through the spin chain. So this is an MPS simulation done at the real infinite temperature OTOCs so that we see what these guys look like in real simulations. So you can see that this travels through the Rydberg atom chain and then bounces back. And then if you calculate the slope of this line, it gives you something around 0.3. The next step is doing this on the simulator. So we did this on the simulator that's provided by Kira called blockade simulator. It does capture the right characteristics, even the second bounce that you see here. But there's some mysterious things going on here where the simulator actually kind of breaks down and then it's just completely unreliable where it should be 0, but you see 1s. However, if you compare the slopes that you obtain from these two methods, they agree very well within the error bars. So the next big question is, can you see this on the actual hardware? And the answer to that is, yes, you can, up to some time. So this captures the initial decay of the OTOCs actually pretty well. And if you fit a line through here and compare it with the other methods, you see that slopes all agree within the error bars. However, the second bounce that you see in these two other methods are not present in the hardware. And the reason for that is when the signal reaches this 8 spin, we're almost towards the end of our coherence time. So it's very hard to kind of reliably resolve the second pulse given how long our coherence time is. So the heat map plots could be kind of misleading. So let's look at them side by side and compare actual numbers. So this is site 8 where we implemented that large detuning pulse. The blue line here is the MPS simulation, green one is blockade, and the orange one is the hardware data. You see that except this first point where we implemented that large detuning, which is not present in the MPS simulation, the hardware actually agrees better with the MPS simulation than the blockade simulator. And then if you go on to the other sides, you see that the agreement between all three things are actually pretty good up to the first three sides. And then it starts to degrade as you go towards the other end of the chain. You still see some characteristic behavior going on with the initial decay of the OTOC, but once you reach the last side, you're almost at the end of the coherence time and you see almost no dynamics going on. So the next question is, does error mitigation improve these things? And the answer to that is, it improves some things, but also makes some things kind of worse. So it makes this area a little bit more clear that you can now maybe imagine seeing the second bounce coming up here. But it's also removed some of your points from your light cone that was present in the first place. So it's hard to justify it, calling this a light cone where with the line through that. I mean, if you do the slope still, I agree within the error bars, but yeah. Take for a minute, let you can. How much time do I have left?
I have 8 minutes total,
8 minutes
including
total.
questions.
Okay, so I can keep going.
Yeah.
So I only show this protocol for one set of parameters, right? What if you change atom distance? So that's what we did here. These are just simulators because we already wasted our shots preparing these plots, but you can test them on the simulator now. So the most important thing, I guess, in this protocol is the atom distance, because that's what controls the next to nearest interactions. And once you go to the smaller distances, you cannot use the randomized quantum procedure parameters that you fine-tune for another parameter again. So when you fine-tune this for 9.5, you can use them for 9.2, 9, and in the close vicinity. But if you go to anything smaller, you need to start this whole process again and fine-tune everything. So what if we change omega, which is another parameter in the Hamiltonian? You see that if you change omega, it is much more, I guess, reliant to the changes on omega. So you can go up to 1.5 and 2, and you can still capture the characteristics of the light cone. You might be thinking like, these actually don't look right. But if you compare it with the tensor network results, you also see that actually the shaded area inside is much more lighter than what you would expect. So the simulator is actually making a good job in capturing those behaviors as well. So your intuition might be telling you, oh, it needs to be as dark as it gets, but you just need to go back and check with the tensor network. Okay, that's me. All right. So if you adjust delta, the same kind of story follows. And you can play with it up to like plus minus 5 on the any kind to the left and right side of your optimized parameter, and you still see similar characteristics. So if you compare, so this is 2.5 megahertz now, and you see that it looks like there's no dynamics going on here, but if you compare it with the MPS simulation, you see that it captures the actual dynamics that's going on in the Rydberg Hamiltonian pretty well. So I'll go back to my conclusions. So we demonstrated the first measurement of OTOCs that uses a randomized analog protocol without the need of backwards time evolution. Our results show very good agreement between its tensor network counterparts, showing that we can capture the infinite temperature characteristics of these OTOCs operators pretty well. And this measurement protocol opens up possibilities of investigating information propagation and quantum chaos in the exotic regimes of the Rydberg Hamiltonian, which is a very interesting area to kind of pursue, where we do not know how these different phases and different kind of connectivities in the Rydberg Hamiltonian will affect quantum chaos and information propagation. So the next thing to do would be to come up with a better ways of optimizing this quantum procedure. So you just give it the control parameters you need, and it finds you a pulse sequence. And there's some ideas on to do that, maybe using some reinforcement learning, using the tensor network data to train your neural network. But so yeah, here is our results, and thanks for listening.